Hello everybody, welcome to the first notes of Unit 5. This unit is called Analytical Applications of Differentiation. Last unit was all about contextual applications, so like real world. This is going to be more about connecting the first function to the derivative to the second derivative and just the way that all those things connect together. And so the first thing we're going to talk about today is a new theorem. It's called the mean value theorem. So far this year you've learned about the intermediate value theorem, which is kind of essentially if you want to get from one number, so say you want to get from 1 to 5, you got to get through 2, 3, and 4. That's kind of the basic principles of the intermediate value theorem. Today we're going to learn the mean value theorem, and then later this week we'll learn the extreme value theorem. And so the mean value theorem says, if a function is continuous on a closed interval and it's differentiable on the open interval, so real quick I'm going to draw a picture that meets those. So I'm going to just draw... Okay, so I'm going to draw just my little tiny coordinate plane. And so let's say we have a function that is continuous and differentiable. So that means there's like no holes, there's no jumps, and then you could take the derivative at all the points. And if you remember, like if you're looking at the graph, the way that you can tell if it's differentiable is if it has a vertical tangent, if it's not continuous, or if it has a sharp point. And so I'm just going to draw like a pretty basic line. Okay, so that's this function right here, as you can tell, is continuous on all intervals, and it's also differentiable on all intervals. So if that is true, if it is continuous and differentiable, then there exists at least one number c in the open interval AB. So I'm going to make an open interval. I'm going to call this A. I'm going to call this B. So it says that then there exists at least one number c in the open interval such that, and so this is the theorem, f prime of c equals f of b minus f of a all over b minus a. And I want you to take a second and recognize what is that saying, because that's what it's saying in notation, but what does that mean in words? So try real quick to think about that. But if you thought about it, you could pause this, but this is what this means, right? F prime of c means the derivative at c. And then over here, f of b minus f of a over b minus a, well, that's the average rate of change formula, specifically the average rate of change from b to a. So what this is saying is that there has to be a c value such that the derivative at c is equal to the average rate of change between a and b. And so let me show you what that means. So basically, essentially what that's saying is that there's going to be some value c. So real quick, let's take the average. I'm going to move my a over just a little bit because I think it's going to help us. So let's pretend that this is the function. I'm going to move my b over too, just so I can draw this picture a little bit more clearly. So the way that you would find the average rate of change between a and b is you would just do the change in f of b minus the change in f of a over b minus a, which essentially is just the slope formula between these 2 points right here. And so essentially the average rate of change is just the slope of that secant line. Okay, so it's the slope of the secant. And what this formula is saying is that, okay, that's the slope of the secant. There's going to be some value c where the derivative at c, aka the slope of the tangent line, is equivalent to the slope of the secant line. And if you look at those two lines right there, they are parallel to each other, which means their slopes are the same. And so the derivative at c is equivalent to the slope of the tangent line. And so we're going to kind of practice this more when we are in person, but essentially what this is saying is that if you have an average rate of change, there's going to be a value between the two endpoints of that average rate of change whose derivative is going to equal the average rate of change. And so average rate of change from a to b, that's going to be equivalent to the derivative of some point between a and b. And that is what that's saying right there. And we're going to continue to practice this concept. But big idea, slope of the tangent is at some point is going to equal slope of the secant line. So let's go on to a couple problems where we're just talking about, does the mean value theorem apply here? So our two conditions for mean value theorem, if it is continuous on the closed interval, and then it is differentiable on the open interval. So the difference between closed interval and open interval means like closed interval means that there has to be a point at the endpoints. And so this is asking, does the mean value theorem apply from 0 to 4? And the answer is yes, because there's actually a point at 0 and there's actually a point at 4. But if there had been like holes in the graph right here, so say like this function approached 0, so it approached 0, but it never really, so say it approached 0, but it never actually got there, and it approached 4, but never really got there, the answer would be no to it being continuous, because it has to be continuous at 0 and 4. So this is continuous, so that part is good. And then the question is it differentiable? So there would be allowed to be holes here, and it could still be differentiable, like it would still pass because it says open interval. So like if there had been holes at 0 and 4, we would say yes, it's still differentiable. But the problem we run into here is this right here. That is a sharp point, and you cannot take the derivative at a sharp point because the pattern of the slope isn't the same from the left and the right side. So the answer to this one is not differentiable because there's a sharp point at 2, and so because of that, you cannot use MVT because that condition does not apply. So you cannot use the mean value theorem. Okay, example 2. Does the mean value theorem apply? So if you look at this function right here, this is a polynomial because it's x cubed. Everything about polynomials and like lines and quadratics, they're all basic. You're never dividing by anything. There's just like nothing complicated going on in a polynomial. And so the mean value theorem does apply. So I'm going to write yes because polynomials are continuous and they're differentiable on all intervals. And that's the same as a quadratic. A quadratic and a line are technically polynomials. It's just polynomials to the degree 1 and then polynomials to the degree 2. It's just like we talk about it more specifically than that. But so any like pretty basic function like this, the answer is yes. The mean value theorem is going to apply because it's continuous and differentiable on all real numbers. There's never anything funky going on with those graphs. Okay, so let's do just like an informal example so you guys can kind of understand more about like what does the mean value theorem actually mean. So here's an informal example. It says Vicky lives 150 miles from the beach. She leaves home at noon, so 12, right? And arrives at the beach at 3 p.m. What is the average rate of change of her distance traveled in miles with respect to time in t-hours? So average rate of change. So we're just using the slope formula here. We just want the change in her distance over the change in her time. So change in distance over time. I also could have put change in d over change in t. So that's what we're looking for here. And so the change in her distance is 150 miles because she starts at her house and then she gets to the beach. So the change in her distance is 150 miles. And then the change in the time is 3 p.m. minus 12 p.m. So minus 12 p.m., which is 3 hours. So we get 150 over 3, which equals 50 miles per hour. So her average speed on this trip is 50 miles per hour. And so what the mean value theorem is saying is that if the average if the average rate of change of her trip, if the average speed is 50 miles per hour, what the mean value theorem is saying is that at some point, Vicky was driving exactly 50 miles per hour. Because if let's say she was driving 40 miles per hour at some point, and then she was driving 60 miles per hour at some point, that would average out to be 50 miles per hour. But for her to have gotten from 40 miles per hour to 60 miles per hour, she would have had to go through 50 miles per hour. And so that is what the mean value theorem is saying. And it honestly is really similar to the idea of the intermediate value theorem. It's just with rates of change and derivatives instead. And so driving, because, and the mean value theorem applies here because driving in a car is continuous, right? You're not skipping over distances and there's nothing too funky. You're not about driving a car. It's also differentiable. You are always moving. There's nothing weird. It's just like a pretty consistent idea of a function. And so because driving a car is continuous and differentiable, the mean value theorem says that at some point Vicky was driving exactly 50 miles per hour. 50 mph. So that is the concept of mean value theorem with kind of a real world situation. Okay, here's the next problem is kind of more like of an application of like, okay, well, what are these problems that we look at with the mean value theorem really going to look like? So This says determine all the numbers C which satisfy the mean value theorem for the following function. F of x equals x cubed minus 9x squared plus 7x on the interval -3, 6. And so we know that the mean value theorem is going to work here because one tells us to use it, and because this is specifically, it is a cubic function, but that's a polynomial. And so we want to figure out what is the C value. So like, remember, this is the formula, f prime of C equals f of b minus f of a over b minus a. So we want to figure out at what specific C value is the derivative equal to the average rate of change. So that's kind of our end goal, is to figure that out. So we're going to start by finding the average rate of change, because remember, if you ever see something like this on brackets -3, 6, those are always x values. So that's the interval. So we want to find the average rate of change from -3 to 6. And so we're going to start with that, because before we can solve for C, we have to know what we're trying to get f prime of C to equal. So I'm just going to put it in the average rate of change formula, f of 6 minus f of -3 all over 6 minus -3. And we're just kind of plugging things in here. So I'm going to try to go through this quickly. It'll be 6 cubed minus 9, 6 squared plus 7 times 6 minus -3 cubed minus 9 times -3 squared plus 7 times -3. Really be careful with your negatives. Remember, if you square a negative, it becomes positive, and then this denominator is going to be 9. Then I will have 216 minus 9 times 36, which is 324. I did this earlier, so I didn't just know how to do that in my head. 7 times 6 is 42. Minus -3 squared is -27. 9 times 9 is 81. 7 times -3 is 21. Again, all over 9. Just plug these in your calculator. The first function will end up being -66. This will be minus -129. So it will come out to be 63 over 9, which equals 7. And I did that really quickly for just the sake of time, but feel free to do that on your own. But 7, therefore, this is the average rate of change. I'm going to write ARC, average rate of change. And so that is what we're trying to figure out, like, when does our function's derivative equal 7? So my goal now is to figure out f prime of C, when does that equal 7? And so to figure out what that C value is, well, first I am going to need to find the derivative. And I'm going to take the derivative, and I'm going to use C instead of X when I take the derivative, just because that's the way that this function notation is used. So the derivative of f prime of C equals, so I'm going back to this right here, the original function. I'm just taking the derivative of that, but when I do that, I'm going to use C instead of X. So it's going to be 3C squared minus 18C plus 7. So that's the derivative, and I'm going to set that equal to 7. And I'm going to solve for C. So that's my goal. These 7s just cancel each other out right away. So now I have 3C squared minus 18C equals 0. And that's a quadratic, so I'm going to factor. And if I look at 3C squared and I look at 18C, they have so first it's only 2 terms, so I don't need to like factor in the traditional way where you'd have like x plus 3 times x minus 2. I'm just going to factor out the greatest common factor, which is 3C. So I'll have C minus 6 equals 0. And then I'll set both of those equal to 0. I'll get C equals 0 and C equals 6. And those are my 2 answers. So sometimes there's going to be more than one C value that satisfies the mean value theorem. And in this case, C equals 0 and C equals 6 satisfies. Okay, we have 2 more examples, and then we will be done. Oh, 3, sorry. Okay, but we'll go quick. So determine all the numbers C which satisfy the mean value theorem. So feel free to start this on your own because it's the same exact concept as last time. So I'm going to start by finding the average rate of change. I need to do that for all of these problems. So it'll be f2 minus f of -1 over 2 minus -1. I'm going to work this out in my head. I'm not going to talk out loud. So I did that pretty quickly, so pause if you need more time, but the average rate of change is 1. And so now I'm going to find f prime of c, and that equals 3c squared over 3, and the 10 goes away, so, and then these 3's cancel out, so basically c squared. And then I'm going to do c squared, because that's the derivative, and I'm going to set it equal to 1. There are two things, so when you take the square root of both sides, you weren't doing this as much, like when we take the square root of both sides when we were doing Unit 4 and we were working with triangles, you always just took the positive answer because distance is always positive, like physical measurements are positive. But in this case, there are actually two answers. When you take the square root, you're supposed to take, like when you take the square root of the number, you're supposed to do plus or minus, because there's two things that satisfy c squared, and that would be c equals positive 1 and also c equals negative 1, because negative 1 squared is 1 and positive 1 squared is 1. And both of those are in the interval between negative 1, and so those are our two answers. So C satisfies the mean value theorem at 1 and negative 1. Okay, two more examples. Example 6, let the function given by f of x equals 5 cosine squared of x divided by 2 plus the natural log of x plus 1 minus 3. The derivative of f is given by f prime of x equals negative 5 cosine of x divided by 2 times sine x divided by 2 plus 1 divided by x plus 1. What value of c satisfies the conclusion of the mean value theorem applied to f on the interval 1, 4? So we're going to read through all of these before we actually do any work, okay? So 2.132, because f of 2.132 equals f of 4 minus f of 1 over 3. So real quick, let's just like set up the mean value theorem. Says f will say f prime of c equals, the interval is 1 to 4. So it will say this, okay? And then we're essentially just trying to figure out what this value is right here. There's a problem with this. Feel free to try to identify it real quick, if anybody sees it. Okay, the problem is this is not a derivative, so this automatically can't be the answer, because the mean value theorem is always the derivative, right? It's the derivative equals the absolute value, or the derivative equals the average rate of change, not the original function. So that one's out. 2.749, because f prime of 2.749 equals f of 4 minus f of 1, which equals 3. So that possibly could be right. I don't see like anything wrong right away. 3.042, because f prime of 3.04 times equals 0. So the question would be, is this the average rate of change? And so we'll get there in a second. And then the last one is 3.252, because f prime of 3.252 equals f of 1 plus f of 4 over 2. So this over here is just not the average rate of change formula. One, there's a subtraction sign in there in the average rate of change formula, and also 4 minus 1 is 3, not 2. So we can take this one away. And so now we're debating between B and C. We don't actually have to do any work besides if C is true, that's the average rate of change. So let's check to see if the average rate of change is 0. And I am just going to kind of skip ahead here. So I just want you guys to put this in the calculator. So I'm going to go ahead and simplify that. But if I plug in 4 here, I'm going to plug in 4 here into the calculator real quick. Do it now. Okay, so that f of 4 equals 3.6. I'm just going to be kind of quick with it, so I'm not too concerned about like whether that's exact or not. And this equals 2.69 over 3. And if I subtract those, I get 0.91 over 3. And that is 0.3. So that doesn't equal 0. And so this one's out. And so by process of elimination, that has to be B. So that's how you would do that one. One more, and then we're done. Okay, this one's kind of a trickier one, but it's fun. So suppose that we know that f of x is continuous and differentiable on 615. So just based on that information, you can use the mean value theorem. That is like a big clue. If you get those two pieces of information, that's a big clue that you could use the mean value theorem. And so we know that this function is continuous and differentiable on 615. Let's also suppose that we know f of 6 equals negative 2, and that we know that f prime of x is less than or equal to 10. What's the largest possible value for f of 15? Okay, so what we know based on the mean value theorem is that this is true. F prime of x, or c, but let's just use x, is going to be equivalent to f of 15 minus f of 6 over 15 minus 6. So the mean value theorem tells us that is true. I'm going to simplify it real quick because I can go ahead and simplify the numerator, or the denominator. So I know that this is true, okay? One other piece of information I know is that f prime of x is less than or equal to 10. Okay, so I know that that piece of information is true. So I'm going to go ahead and use that in this problem. So if f prime of x is less than or equal to 10 and f prime of x equals f of 15 minus f of 6 all over 9, then I know that this has to be true. I know that f of 15 minus f of 6 all over 9 has to be less than or equal to 10. I also know that f of 6 is equal to negative 2. That simplifies to this. Okay, and I just want to figure out what is the largest possibility that 15 could be to make, or f of 15 could be to make this true. So I'm just going to solve for it. Multiply 9 on both sides. I'm going to get f of 15 plus 2 is less than or equal to 90, and I'm going to subtract 2 on both sides. I get ignore that, f of 15 is less than or equal to 88, so the answer is 88. And now we're done. Thank you guys for sticking around. So this is just like an example of when, besides like a normal find the C problem, like when you could use the mean value theorem. Thanks for listening.